Dear students, welcome and thank you for tuning in for another video. In this video, we are continuing our discussion about ceramics as part of the material science class and the biomaterials class. In this video, we are going to discuss crystallinity and whether ceramics are crystalline or partially crystalline. If we remember from our discussions and lectures about metals, when we were talking about crystallinity, we were talking about the unit cells, how atoms are arranged in repeated units inside the material. So if you remember from metals, we said we have something called cubic unit cells, and we called them, face center the cube or body center the cube. And so we when we talk about crystallinity in ceramics, we will revisit the same concepts and definitions that we used and parameters we used when we were talking about metals. So let's dig into this. So just like in metals, we have something called a unit cell, that is an arrangement of atoms that repeats itself inside the material. That's the same thing happen in ceramics as well. So ceramics are also made of units of cells, and they used to describe the characteristics of atomic arrangement in the ceramic. So how atoms are arranged and how many of them and in which orientation give us decide the characteristics of the ceramics. So in ceramics, the cubic and hexagonal cells are most common. And there is an important aspect here. If you remember, when we discussed metals, we talked about the coordination number. And the coordination number is the number of atoms that touches a particular atom inside my unit cell. That is making, this unit cell that makes repeat itself and makes up our material. So here in ceramics, the difference in radii is very important. So if you have atoms that touching each other, the difference between this atom, let's say the radius of this atom and that atom, is important in ceramics because it affects its properties. And we will talk a little bit more about it. So the radii between metallics and the differences between metallics and non-metallics, metallic ions plays an important role in the arrangement of the unit cell, and resulting in changes and in the properties of the material itself. So in metals, if you remember, the regular arrangement of atoms is into densely packed planes, and these planes they were moving, slipping, and sliding. And this, because we have these planes, we had something called slipping under stresses, and that resulted in the plastic deformation and gives the metal its ductility. And that's how we are characterizing metals. However, in ceramics, on the other hand, we know that we have this arrangement of atoms, but we don't have slip and slide planes because the atoms are ions, and we have ionic bonding. And ionic bonds are different from metallic bonding in such a way that it does not allow for dislocations to move or atoms to move and to create plastic deformation. So ceramics, if a ceramic was exposed to loading and that exceeds its ultimate strength, it will have a brittle fracture rather than slipping. So no plastic deformation, and that's because the arrangement of the atoms and the types of bonding is different. So in metals, we have metallic bonding, and we have different structures or planes for our cells, the unit cells. In ceramics, we have ionic bonding, and it's very hard to move the dislocation or the atoms because of the ionic nature and the bonds itself. I want to discuss more the importance of the radii of them element. So if in a stable ceramics, if we have a material and that's a ceramic, and we can call it a stable ceramics, the ceramic structure, we have anions and cations, and in order to create your ionic bond, so you need to have a positive ion and a negative ion to create the bonding that will be a characteristic of a ceramic. So we know that we have the cation is in the middle, that's a positive, and the anion is the negative. So the usually the arrangement in ceramics that you have a positive ion and then you have surrounded by negative ions. And in order to have a stable structure in ceramics, the anions need to touch the cation, right? So this is stable. This is another stable structure. You can see there is touching between the negative ions and the positive ion, but this one here we don't have touching, which means that this is an unstable structure of the ceramic. Now, in order to quantify this, it's important to know that we have something called the coordination number, which is the number of atoms touching a particular atom. So for this case here, the first case to the left, the coordination number is 4, because we have 4 atoms that touches this atom here. 4 anions touches the cation. Here the coordination number is 0, so it's unstable. There is no touching with this one, with this atom. And in order to give more, other than the coordination number, there is a ratio, which is the critical, called the minimum cation to anion radius ratio. And this ratio, which this contact is stable and can be maintained. So there's numbers that we need to look at in order to see if my structure is stable or not. So for example, in this schematic, you can see that if I have a coordination number of 2, the ratio for the cation, or the radius of the cation divided by the radius of anion, could be less than 0.15, because one from this side and one from the other side, the cation is the one in the middle, it's small. The radius here divided by the radius of this big anion is going to get us something less than 0.15. So this is a stable structure. This is stable geometry for ceramics. Now, if you have 3, the coordination number is 3. So your unit cell has 3 atoms and that touches 1 atom. So you have this cation and we have 3 anions. The ranges of your appropriate ratio that you will end up with a stable structure is between 0.15 and 0.225. Sorry, there is a missing dot here. It's 0.225, and you can go up to if you have 8, the coordination number is 8, the 8 atoms that touches 1 atom, it means that your ratio of the cation, the radius of the cation to the anion, has to be between 0.731 to 1.0. It's a lot. So this is we're trying to quantify things and we give some numbers and understanding for ceramics. Keep in mind, ceramics are made of ionic bonding mostly, and you have a cation in the middle and you have anions surrounding that cation. The ratio of the radii of the cation to the anion is an important ratio to determine stability for ceramics. It's very important. One more thing, with ceramics, unlike metals, they're difficult to shear plastically, so you can't have slipping and sliding. It's very hard and even near to impossible in specific planes. So in this plane, it's impossible to have shear plastically due to the ionic nature of the bonds and the small number of slip systems. So we don't have a slip system here. Let's say if you took this line here, if you need to slip or slide, the positive ion will be in contact with the positive ion. This is going to create repulsion, so that's very hard to happen. It's impossible to happen, and this results in the brittleness. So the brittleness originates in the constraint imposed on the possible slip plane because of the repulsion of the ions, positive and negative ions. This is different from the metallic bondings, and you can see this in a much picture in 3 dimensions. So if this is a ceramic and you have the purple as positive and the blue as negative, if you need to slip in this direction and that direction, so if you're pushing this way and that way, slipping will happen, which means that the positive will be with the positive, and that's going to create repulsion, and that's not a good way to have movement, and dislocations will not move. That's why ceramics are brittle, because they do not allow for plastic deformation or slipping. However, in some certain cases, dislocation motion is possible, but it's very difficult because it has to be in a specific direction of plane that are not in the most close packed. So if you look at this plane here, you can see that you have negative, 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 and you have positive, positive, positive ions. So slipping in that direction is possible, but it's very hard. So I hope this is giving you a good idea about ceramics and its crystallinity, and what are the properties and the parameters that we can measure because of, or related to crystallinity and ceramics. Thank you for watching. Until next video. Bye.